Good day, friends. Today we're going to discuss something very interesting called dispersion of light. This is not something new. In fact, this is the thing that you maybe have seen on the internet. Maybe you see it in your daily life. We're going to discuss about that. And I probably suppose that you already did. Okay, so what is dispersion itself? Dispersion, in simple words, is splitting white light into different colors. Yeah. So as you can see here, we have some beam of light. Yeah, white light, which goes to some kind of a prism. Yeah, prism is just this kind of a glass or maybe some different material, right? And when we pass our light at a certain angle to the normal, yeah, for example, we have a normal from here, yeah, then we can see that we have this kind of phenomenon. It breaks down into 7 different colors, and these colors are called Roy-G-Biff. Yeah, this is exact order from the highest wavelengths, which is the red one, and to the lowest wavelengths, which is violet. Okay, so if red has the highest lambda, then it means that it has the lowest frequency and the lowest energy, right? And violet has the lowest lambda, highest frequency, and highest energy, yeah? Because due to Max Planck's theory, the energy of an individual photon is hf or hc divided by lambda. As you can see here, lambda is negatively proportional to the energy of the photon and frequency is positively. Okay, good. So these colors are red, orange, yellow, green, blue, indigo, and violet. Okay, so this is the order that our white beam of light will split. Okay, so to understand why this phenomenon happens, yeah, we said that right now dispersion is splitting of white light into different colors, but the question is why? We need to understand it, but before we understand it, let's first talk about the coefficient of friction. Yeah, so it is a strange thing. In fact, you might think, why do we need coefficient of friction in optics? It is the mechanics thing, and you will be totally correct. However, let's try to think critically. It will help us to understand something very important in optics, but first let's try to understand coefficient of friction. So every time when we say that steel has coefficient of friction, something like that, this, yeah, or wood or glass, in fact, it is not their coefficient of friction. They cannot have their own individual coefficient of friction. Instead, we have something on something. For example, steel on iron, or wood on concrete, glass on ice. What does it mean? It means that if you make two things have a contact with each other and then move in different directions, then they will experience different sort of mu, which is the coefficient of friction. So if we take the steel, it has a different friction with iron, it has different friction with concrete, it has different friction with ice. The same thing goes for wood. It's different for each one of those things. Or glass, if we take some glass, it experiences different friction force with this one, and with this one, because the coefficient of friction for each of those things is different. Yeah. Okay, so what we can understand from this, we don't have individual coefficient of friction for certain materials. Instead, we mean by that that two objects have this kind of coefficient of friction related to each other. Okay, so it's the factor which depends on two things, on two materials. Okay. Right now, let's return to optics. We have something called index of refraction. If you remember this is the n, which we use in our Snell's law, if you remember, n sine theta equals n sine theta. Yeah, but it's the medium 1, this is the medium 2, this is index of incident line, this is the angle of refracted line, yeah, or our beam of light. Okay, so why did we need this coefficient of friction? Because it has almost the same idea. The idea is next. We don't have individual factor for one thing. Index of refraction does not it has nothing to do with the individual color, some light. It is not index of refraction for red color, for violet color, for yellow, and so on. Or we don't have index of refraction for some certain medium. It is not for water, it is not for glass, it is not for something. In fact, index of refraction, it is again the factor which depends on two factors, right? So it is index of refraction of some certain light in a medium. So if you take some red in a glass, yeah, for example, our medium would be glass, it will experience different index of refraction. If you take violet, it will experience, at the same glass, it will experience different index of refraction, okay? If you can see here, yeah, white light goes to the prism and then it breaks down into 7 different colors. We can also say that if we collect those 7 colors together, then they will give us white light. So it is a reversible process, right? Okay. By that, we can understand that in this prism itself, this is some glass or some different material, does not matter, but it's entirely one material. And as you can see, each of the colors, they experience different kind of index of refraction. They refract differently because they interact differently with the same material. Okay. Right now, let's try to understand the nature of white light. White light is a mix of all colors. So it is not something by itself. What we mean by white light, it is the wavelengths which are mixed with each other. As you can see here, we have red, which is the longest wavelength. We have violet, which has the shorter wavelengths. As you can see, it's definitely shorter than red. For example, look at this one. This is the violet, which stops here, and you can see here a red, which stops here. And it's pretty much logical. Why? Because red has a wavelength. Yeah, lambda of red is 760 nanometers, and lambda of violet is 380 nanometers, which is twice as low than red, right? And as you can see, in one wavelength of red, you have two wavelengths of violet. This is one wavelength of red. This is two wavelengths of violet. And it's pretty much logical. So if you mix all those wavelengths, then you will have white light, okay? Good. So let's talk about this one. Speed of light in the different mediums. You might think that, well, it's very simple formula. It's very easy. Yes, it is easy. In fact, it is easy to understand. However, the meaning of it is interesting. The meaning of this thing is that the velocity of the light, yeah, as you can see, it depends on the medium that it is in, right? So C, the speed of light, will be constant for all colors. So if you take, for example, the red laser or green laser, they will experience the same speed because they all have the speed of light, okay? They will not be slower than this. They will all be the same speed, but in the air. As we add something, yeah, some sort of a medium, then different for each color, as they interact with the medium differently, okay? So what does it mean? Each of the colors, they interact with some certain material by themselves. So for example, look at this one again. You have white beam of light, which splits into different colors. And as you can see, well, this red will experience less index of refraction, right? So which means that it is faster. And this violet will experience high index of refraction because it refracts strongly than red one, as you can see. So our initial direction is something like this, and our red, in fact, it refracts a little bit like this, just a little refraction. Violet refracts like this. You can see that it is high refraction, yeah? It has a high deflection compared to its initial direction. And if it is so, it means that its index of refraction is low, and if we know by that formula that speed of a certain color in a medium is C divided by N, and if the N is low for red, it means its velocity is high, and if velocity, yeah, it is red, it is violet, then it will be something like this. The index of refraction for violet is high, which means its velocity will be lower, right? So it is slower than the red one, and we can see it here. Higher the N, slower the light in a medium. So if the index of refraction, if light bends strongly in some sort of a medium, then it will be slower than other light, yeah? So violet is slower than red in different mediums. We can see it because its index of refraction is always higher than red's. That's why its velocity will be lower, okay? Let's look at this one. So basically, what do we mean by high index of refraction? We send light with a certain angle theta to the normal, and both red laser and the violet laser, they will have the same angle of incidence, yeah, which is theta and theta. Okay, but as you can see here, the deflection of red, or better to say refraction of red, it is lower than the refraction of the violet. So you can see that compared to its initial direction, this one, violet experiences high refraction. It bends strongly, and the red one, it bends. Of course, it bends. Of course, however, the difference compared to the violet, it is definitely not that much. Okay. Basically, you see dispersion in your daily life. I have drawn here only 3 colors, yeah, because I don't want to write all the time 7 colors, and it would be too much. But 3 colors would be enough: red, green, blue, the basic colors that human being sees. And we can see this phenomenon. In fact, you just imagine that here we have other colors as well. Some certain drop of the water, it falls from the sky, and that thing what we call rain, right? And when we have, for example, our daylight, yeah, and it pierces through our water droplet, then it will experience dispersion, because this is the water, right? It is some sort of a medium. It has some index of refraction, but it's different for red, it is different for green, and it is different for blue. Why? Because each one of those colors interacts with the same medium, which is our water droplet, differently, yeah? As you can see again, red deflects compared to the initial direction, not that much. Violet or green deflects stronger. As you can see, it's higher angle. And here we have the strongest bending, like this. And it is pretty much intuitive because it has highest lambda, this has medium, yeah, something in between, let's say, and it has the lowest lambda. Okay. And then you see this phenomenon in your daily life, which is the rainbow, yeah? So this is how rainbow appears in the sky. So you need 2 factors. You need a droplet of water, yeah, the rain, and the second one, you need daylight or any sort of light, because you can never see rainbow at night. It has something to do with the sunlight or other source of light. Okay, good. So let's talk about aberrations. Last time, when we talked about the lens maker, if I'm not mistaken, we have discussed about spherical aberrations. Yeah, there are several types of aberrations, and let me remind you that aberrations are any imperfections in the image formation by lens or mirror. So what was the problem with spherical aberrations? The thing is, we have, for example, this gray one is our axis and our converging lens, and by definition of focal point, it's the point where parallel rays of light meet with each other, right? However, the problem about it, yeah, imperfection, what's the problem with this light? The thing is, we have this kind of parallel lights, which are the same distance, right, from the axis. They collect at a certain point, for example, this point. However, if we take other parallel rays like this, then its distances from the axis are a little bit far, and they collect at a different point, right? They meet at a point which is a little bit closer to the lens, and the which are the farthest, they collect at a different point. If we had a single focal point, yeah, for all parallel rays, it would mean that at a certain point we would see a dot of light. This one, yeah, for example, if we put screen over here, we would see something like this, yeah. If we put screen over here, we would see light like this one, okay, good. Or if you put it here, you would see something like this. So it is not a certain dot. The problem with spherical aberrations, it's a problem with spherical lenses, and the problem is that not all parallel lines meet at the same point. Yeah, so they meet at different focal points. That is the problem about lenses. We also have chromatic aberrations. So it's the problem of the lenses related to the colors, right? Let's say we have a point source of light. In fact, here we have many other rays, yeah? But let's take the two extreme of them, the edges, yeah? And if we send here two the very extreme lights at the very edges, then you can see that at a certain point, they deflect into different colors. Yeah, the blue will collect at a different focal point. The green one will collect at different focal point, and red one in different focal point. Yeah. Okay. Of course, we would see here some difference between two focal points. Here again, some delta f1. Here we would see some delta f2. So you can see here that we would see different colors being collected in different points. Yeah. So as you can see here, we have written right over here, the lens fails to collect wavelengths to one focal point. As you can see, different wavelengths, we mean different colors, and we expect them to be collected as one white light, yeah, and it would be a point, but as we have told you before, it would not be a point, yeah, because they have different focal points. The same thing goes different focal points for different colors. So lenses fails to collect all wavelengths to one focal point, okay? The next thing is called Rayleigh scattering. It is something like this, some very simple formula, intensity of light equals 1 divided by lambda at the fourth power, which means that the higher the lambda, the lower the intensity. Or if the lambda is lower, then intensity is higher. Yeah. So what do we mean by that? It's something that you see in your daily life. The question why sky is blue. Yeah. It just scatters. Yeah. As you can see, we have written here Rayleigh scattering, which means that white light scatters into different wavelengths. Of course, you know that the shortest wavelength is violet, and which means that if it is the shortest wavelength, the intensity would be highest. Yeah. So our sky must appear in the violet form. However, it is blue. What's the problem? Because our eyes adapted to see better a blue color rather than violet color. Yeah. That's why our sky is blue, because it is the most natural color with the lowest wavelengths that we are adapted to see well, yeah, and that's why the intensity of that color would be higher at the sky. Yeah, of course, there is also a red color at the sky, even at the midday. Yes, the sky could be red, the sky could be orange. It's okay, but the blue light scatters more as its wavelength is smaller. Its intensity would be higher. That's why our sky appears to be blue. Yeah, the shorter wavelengths, higher scattering. Yeah, okay. The next thing, let's talk about dispersion in parallel surface glass. Okay, what does it mean, parallel surface glass? Yeah, it is something like this, which means that if we have some sort of a glass, some kind of medium, then the two surfaces have to be parallel to each other. They must not meet at some point. We have also non-parallel surface. For example, these two surfaces of the prism are not parallel, because if they were, they would not meet, but as you can see, they meet at a certain point, which is this one. Yeah, let's work with this one. We'd see right now that they would experience dispersion in different ways, in the first situation and the second situation. That's why let's try to calculate it in the form of formula. Okay, so we have some white beam of light, ray of light, going into the glass, and then it would experience dispersion definitely, and then those two colors would come out at the same angle, which means those two would be parallel to each other. Yeah. So violet and red coming out of the glass, they would be parallel to each other. It means that they would have some difference in paths, as you can see. This is delta x, and also it means that during all, if those two are parallel, during all these ways, their distance is the same. So this thing would be delta x. Okay. Okay. So. Okay. Then how to approach this problem? Let's draw here first normal. And we can see here that our red one would experience different angle of refraction. Yeah, and this would be theta r, let's call it. And this one would experience different angle of refraction, which is theta v. Yeah, this one is theta red, this is theta violet. The original one, let's call it just theta itself. Theta, okay? Okay. This is our air, yeah, our n1 equals to 1. And here you can see that we have index of refraction, not for the glass, but how glass interacts with red and how glass interacts with violet, okay? Then, it would mean something like this. To find the meaning of the theta violet and theta red, we would write here Snell's law, n1 sine theta incidence equals n2 sine theta refraction. And our n1 is air, that's why we can cancel this out. Angle of incidence is the same for both of them, and also we have here n2, which is different for our two colors. So for red one, yeah, let me write it here, red, and then I would write here maybe some violet. For the red, it would be something like this. The meaning of theta red would be sine theta red equals sine angle of incidence, the same for both of them, divided by n red. Okay. For violet, it would be something like sine theta violet equals sine angle of incidence, the same for both of them, and this would be n violet. Okay, good. Now we have the meaning of both of them. We can go further and write something like this. The theta red itself would be arc sine. Yeah, this would be arc sine of this value, sine theta I divided by nr. And here we go the same thing. It would be theta violet equals arc sin, and this would be sine theta I divided by n violet. Okay, good, good. Right now we have the meaning of both theta. Okay, then let's try to note the thickness of our material as some h. Yeah, let's call it h. Then we would definitely have what? Our tangent would be this part. Yeah, for example, for violet. Let's define this part as some x for violet and this part as x for red. This entire part would be x for red, and as you can see, our delta x has the meaning of delta x equals x red minus x violet, which is pretty much logical. Yeah. So if we want to find that thickness of our glass, yeah, or difference between, or let's try to find delta x. Let's say we have the thickness of our glass, and we don't have the meaning of our delta x. And to find that delta x, in fact, it would not be something hard. We would do something like this. We have tangent for violet. Let me write it for violet. Or let me write it with red first and then violet. Okay, red one would be what? This would be tangent, theta red, and its opposite would be this xr, and its adjacent would be our h. This would be x red divided by h. And the same thing goes for violet. This thing would be tangent, this different angle of violet. This thing would be x violet divided by h, right? Okay, then we can do something like this. If we throw that h to the side of the tangent, we would have something like this. This would be h tangent theta r. The same thing goes for violet. This thing would be xv equals h tangent theta v. And then if we subtract those two equations from each other, then we would have something like this. Let me write it with white right now. xr minus x violet, which is our delta x, will be equal to h tangent theta r minus this thing, h tangent theta v. And you can see h is the same because it's the same thickness of the glass. We can bring it out, then it would be tangent theta r minus tangent theta v. Okay, so the equation that we would have would be something like this. Let me point it out. This one, yeah. Okay, let me take it and put it back. Let me take this and put it back. Okay, right now we can find the meaning of the delta x if we have the thickness of our glass material. Yeah, let me point it with yellow. And tangent theta r, tangent theta v. We do know this tangent red and we do know the theta red and theta violet because we have written those two right here. You can see it. The meaning of it would be like this. We know from the very beginning the index of refraction for red, index of refraction for violet, and we know the angle of incidence. That's why we can calculate everything and we can find the meaning behind the delta x. What does it mean? In real life, it means that when those two colors come out, yeah, they would never collect together because they would be parallel to each other. And also, the distance between them will keep all the time being just this value. Delta x equals the thickness of our material and the subtraction between two tangents of their angles. Yeah? Okay, good. Now let's try to solve the problem about dispersion in non-parallel surface class. So, as I have said before, we have two surfaces, one surface that accepts the light and second surface that plays the role of exit. Okay, so what we have here is something like this. We have a beam of light and then here we have dispersion again, but we need only the red color and the violet color. And then when they exit the second surface, they go different sides, of course. The interesting thing about this non-parallel surface, what's the distinction between this one and the previous one? The parallel surface glass, the distance between these two will keep being just some delta x all the time because those two are parallel to each other. But when we deal with non-parallel surface, then those two will not be parallel to each other. If we just keep drawing their beginnings, for example, hypothetical, they cross at a certain point, which means that they are not parallel because two parallels can never meet each other. And look at this distance, for example, this distance, this delta x, for example, yeah? And let's try to continue these lines hypothetically like this, yeah? So look at this distance, delta x, and look at this distance, delta x. Definitely those two are not the same, right? So this is delta x1, this is delta x2, which means that this delta x keeps getting larger and larger. They keep getting away from each other more and more, right? So this is the biggest distinction between two of them. A parallel surface, they will keep the same distance, but in non-parallel surface, the difference is that this distance will keep getting larger. However, there is one thing that will not be changing. It is this phi that we need to find. So what is phi? Definitely, if we, for example, take this violet and put it somewhere here, we can see here that there is some angle between them, and let's call that thing our delta phi. Yeah. So it's the angle that it's angle of difference between their deflections. Yeah. And this thing will not keep getting larger. It's the same thing. Only their distance from each other will keep getting more and more and more. However, this angle delta phi will be the same. Okay, all the time. So right now we need to find that delta phi. But right now, first, let's bring back this violet to its place, like this. Okay. So how do we approach this problem? Well, the thing that is happening, let's try to divide this problem into two parts. The first part, when this white light enters this prism and then it goes in, and then when the second part is when it is already inside and it is trying to get out. Okay, two separate moments. Yeah. So what we can find about the first problem, the first part. The thing is, it's the Snell's law. Yeah, we have some medium 1, medium 2, some angle of incidence, which is this one. Yeah, given. We need to find that angle of refraction for both of the red and the violet. The same thing we can do in the second situation, because again, here we have, now it will become our medium 1, this will be our medium 2, and then we need to find angle of incidence and angle of refraction, right? At the very end, of course. Okay, let's try to draw here first normals. I will try to do it as best as I can. For example, like this, yeah? This will be my normal, for example. And let's draw here two more normals. Yeah, right now I like it. And let's copy it and paste it here. Yeah, something like this. Okay, something like this. Okay, what are our situations? Situation number 1, this one. Situation number 2 is this one. Yeah. Okay. At number 1 situation, we have the same angle of incidence for both red and violet because they both come from white light, right? Okay. Then what should I do is draw here this angle of incidence, which will be my well, let's write it straight 50 degrees. Okay. My angle of refraction for the red would be this one. This is theta r. Angle of refraction for violet would be this one, theta r. Okay. What about these lines? Let's continue this red one with orange. Let's continue this violet one with blue maybe, or yeah, why not with blue? Okay, this orange has a meaning of 90 minus theta r. 90 minus theta r. Why? Because this part is 90 degrees. Yeah, that is exactly what normal is. Yeah, theta r. Yeah. What about the blue one? It is 90 minus theta. Oh, no. This is violet. Yeah, this is violet. I'm sorry. This one is violet. and this is 90 minus theta violet. Yep, good. If I can find those two angles, what can I do about it? Look at this one. This is one triangle, and also I have this one more triangle, right? So why do I need those two triangles? I know this angle is 60, right? In that case, look at this one. I know what this angle is. I can find theta r from this one, from Snell's law. And if I know this 60, I can find this angle. If I can find this angle, I can find this angle. So it would be my angle of incidence for the second part of the solution. Yeah, the very same thing goes for this triangle. I can find this angle. Yeah, theta v is found by Snell's law, right? And then in that case, I can find this angle. And then if I find this angle, I definitely can find this angle of incidence for the second part of the solution. Okay? Okay, now what we're going to do is identifying these angles. First, let's call this angle of red like some alpha. Let's call these angle some sort of beta. Yeah. Then in that case, this angle that we need, yeah, let me draw it, for example, with yellow, maybe. This angle would be what? This angle is 90 minus alpha, and that is exactly what I need, because I will work with normal in Snell's law, right? This thing would be my angle of incidence, and this angle would be my angle of refraction, which is exactly my phi for red, right? And that is exactly what we are searching for, because delta phi is, by its definition, it's just phi1 minus phi2, or in our case, just what has larger angle. This is phi violet, this is minus phi red, right? Okay, good. The same thing goes for here. I would take maybe some different color, maybe some indigo, yeah? This thing would be my 90 minus beta, and that is again my angle of incidence for the second part, and I can find here phi for red, I can find it, phi for violet, and then everything would be good, okay? A little bit geometry, of course, maybe you got distracted at some point, but you can reverse the video backwards and then start it again, of course. So what we have here, we can find this theta r. Let's write it with red one. Angle of well, let's write here with white one. The Snell's law. Yeah, Snell's law. I would even write it with like this. So n1 sine theta I equals n2 sine theta r. Yeah, angle of refraction, of course. So our first medium in the very beginning, it's air. That's why we can get rid of it. I would write it straight up. Yeah, for red it would be 1. Sine theta I, it would be my sine 50, some number, definitely. N2. This thing would be my index of refraction for the red in the glass and for the violet in the glass, yeah? I forgot, no, I didn't forget. It's right here and right here, yeah? For the red, it's 162, yeah? We're working with red. This thing would be 162, and theta r would be something that we are searching for, sine theta r, yep? For the violet, it would be almost the same situation. This thing would be 1 multiplied sine 50 degrees equals 166 right now, and multiplied sine theta violet. Okay, right now we can find what? We can find our theta r, and for the red it would hold the meaning of, okay, 162 goes there, and this thing would be arc sine of some sine 50, some sort of a number, divided by our 162. And for the violet, it would be almost the same thing. Theta violet, this would be arc sine. At the top again, sine 50, the same angle of incidence, divided by 166. We can find their meanings. For violet, it's some number. For the red, it's some number. I will calculate it a little bit later, okay? If I do it right now, then I can work with triangles, yeah? Let me take these solutions a little bit here, because I need some space, of course. Yeah, and let me move these two a little bit below. Yep, that would be okay. Okay, two numbers are found. Right now, let's work with triangles. These two triangles, right? So the triangle number 1, we have here 90 minus theta r. We have here 60 and alpha. And those three together must give me 180, right? So for the red, it would be 90 minus theta r. Oops, theta r plus 60 degrees plus alpha equals 180 degrees. Yeah. In that case, if I move 60 there and 90 there, it means that alpha minus theta r must give me 30 degrees, right? Look at this one, yeah? This would be my angle of incidence for the second part. So in that case, I can write for the red something like this. Again, Snell's law for the second time. Yeah, let me write it here. Let me note it here. The first part, yeah? When light enters the prism. And then the second part when light exits the prism, right? So let me write it here. Right now, I'm going to calculate the second part, yeah? It would be something like this. Let me take it and copy it. Let me take that and copy it. Okay, good. Right now, I don't need this. Okay, this would be sine. It would be okay. Okay, not this one. Sorry. So this thing, 162. These things all change. Theta r. This thing. Yep. Good. I like it. In that case, this whole thing is gonna change. Let me take it yet like this one. Yep, good. Okay, I can find alpha from here, but let's not touch it yet, yeah? What I can write here for the Snell's law for the second part, this would be my angle of incidence. Then I can write here my index of refraction for the red would be my first n, yeah? This thing would be 162 again. This thing, let's move it a little bit here, maybe this one a little bit here. So this would be my 162 sine, this would be 90 minus alpha, which is something pretty convenient. This thing is just 1 because it goes to the air, right? And here, what we can find is our phi for the red, and that is exactly what I'm trying to search for. So this would be my phi red, not theta, right? This thing would be my phi for red, and the same thing goes for violet, the same process. Okay, let me take it a bit here. Let's move it here. Okay, yep, good. So this would be my 166 sine, this would be 90 minus beta, and here, this would be my 1 because it goes to the air, sine phi beta. Phi violet, sorry. Yeah, phi violet. This is phi violet. We exactly do know what is sine 90 minus alpha. It is cosine, right? So that's how we can do our life much easier. The second triangle would go like this. Again, this is 90 minus theta v. Let me write it with violet again so you don't mess this up. 90 minus theta v plus 60 degrees and plus beta, right? This would be again 180, the very same process. Then those two go there. This would be beta minus theta v. This thing has to be 30. This thing has to be 30, right? So just in order to find the meaning of alpha, this thing would be what? This is alpha, would be some number, beta would be some number, and we can calculate those. The only thing that we need to do right now is calculating theta r and theta v. Okay, I'm going to do it right now. For you, it would be just instant of time. Okay, theta r keeps going, and this thing would be our arcsine. Inside we would have this kind of number, 0.47, and yeah, that would be 0.27 would be enough. And for the second one, this thing would be 0.46. Yeah, pretty good. Arcsine 0.46. Yep. Okay, then right now, remember these are numbers, not angles, and right now we can find their different meanings. Then those meanings would be something like this one would be 28 degrees. Okay, violet is going to be 27.4 degrees. Yeah, good. Okay, in that case, we can see that alpha is 30 plus theta r, which is plus 28. It would be 58. This thing would be 58. Let me write it here, 58 degrees. The same thing goes for beta. It would be 57.4. This thing is going to be 57.4 degrees. And right now, here we have what? Okay. Sine phi has the meaning of 162. Here, let me write it like this. Let me continue it. Sine, not sine, I'm sorry. This is 162 multiplied cosine. Yeah, because sine 90 minus alpha gives us cosine alpha. And right now we have cosine alpha. The meaning of alpha we know is 58. This is cosine of 58. Yeah, good. And here we have 166. Multiplied cosine again, because the same thing goes here. Sine 90 minus beta gives us cosine beta. And our beta is that thing, 57.4. This thing would be 57.4 degrees. And the rest is just calculation. Let me calculate it very fast. Yeah, one thing to note, I have forgotten that this is sine phi r. If we want to find just phi r, this whole thing has to be arcsine, right? This thing, I have forgotten here, arcsine. This thing is got to be arcsine. This is in the brackets inside. The same thing goes for here. This would be arcsine in the brackets. Okay, inside of that, okay, do I have space? Not much, but I think that this would be enough. This thing would be some arcsine of some number. This thing would be arcsine of some number. Arcsine of some number. This number and is something about 0.86. Yeah, 0.86. What about the second arcsine? It is 0.894. Right? Yeah. 0.894. Yep, that would be enough. So this is some number, this is some number, and let's try to put those numbers in and find our phi. This thing gives us 59.32, this thing is 59.32 degrees, and the second one would be 89.4. This thing is 63 and 38, 63.48 degrees. So as we have said in the very beginning, we need to find delta phi, the angle between them, and our delta phi holds such kind of meaning. Let me write it here. Delta phi equals phi r, phi violet is larger. So we don't need some negative angle because it cannot be. Yeah, and that's why this thing would be first 63.38 minus 59.32. 59.32. So I believe it's something about 4 degrees, 0.06. 406 degrees. That's our delta phi. Difference in their deflection. Yeah, they will deflect in different angles relative to the normal. And that is their difference. Okay, I hope that it was clear to you. I tried my best, but if you have any questions, you can write me privately. Thanks for your attention, and goodbye.